Today we're starting Chapter 9 with Day 1. We are continuing with using trigonometry and building upon our knowledge of the trig functions, their identities, and the unit circle. So if we take a look here at the addition formulas, you want to make sure you write these down and have these in your notes. It would very much help if you have them memorized, but again, if you don't, have them in your notes so you can refer to them until you get comfortable enough to where you do know them. Please take a look and note that the sine of s plus t, notice the alternating pattern with sine, cosine, sine of s, cosine of t, and then the plus, how the addition of two values inside the sine function creates a sum of those values when you combine sine of t, sine of s, cosine of t, plus sine of t, cosine of s, whereas for cosine of s plus t, when you are adding two angles on the inside, notice how for cosine, it is an opposite relationship when you split it into that addition formula. Likewise, if we go to sine of s minus t, the subtraction of two angles inside a sine function, again, we have that alternating pattern with sine of s, cosine of t, but again, they're subtraction, whereas cosine of s minus t, again, you have cosine of s, cosine of s, cosine of t, but then again, it is the opposite when you have that addition formula. So have these down, memorize them. You're going to use them quite a bit. The more you use them and the more practice you get with them, you will feel more comfortable and you will know them. The tangent, you want to make sure you know those as well. Again, there is a similar pattern between the two where, again, you have the same up top, but then the opposite below. And then the right side, when it is subtraction, it is the exact same in terms of what is written. The only difference is, again, same up top, opposite below. So have these written down, make sure you have them. We're going to be using them here in a minute on our practice. Some extra formulas that are helpful as well are the cofunction identities. So cosine of pi over 2 minus an angle is equal to sine of that angle, whereas sine of pi over 2 minus the angle is equal to cosine of that angle. So again, essentially their complement is equivalent for sine and cosine. The reduction formulas, those are also helpful as well. Specifically, cosine of the opposite of an angle is equal to the cosine of that angle, and then sine of the opposite of that angle is equal to the negative sine of that angle. So these two in particular will also be helpful, but all of them can be used. Since these are identities and formulas, you can use these at any point because they have been proven to be true. Taking a look down at the examples, we're going to see how we're actually applying them. Now, for example number 1, notice we have sine of an angle times cosine of an angle plus cosine of an angle times sine of an angle. Notice because all of these angles are on the unit circle, you could find sine of pi over 6. We know that's 1/2 times cosine of pi over 3. We know that is 1/2 as well, and so on. So you can just find those values because there are angles on the unit circle. However, if we notice, this angle here is equal to this angle here, and this angle here is equal to this angle here. So essentially, we have sine of s cosine of t plus cosine of s sine of t, right? Sine of s cosine of t plus cosine of s sine of t. We know sine of s cosine of t, sine of t cosine of s, that is equivalent to sine of s plus t. That's our addition formula identity. So what we can do is we can apply this formula and just say that this whole thing is equal to sine of s plus t, and then plug in those two angles that we have. So that's sine of pi over 6 plus pi over 3. And now on the inside, you end up with sine of pi over 2, which is a little bit easier to find because that's 90 degrees on your unit circle, and the y value at a pi over 2 would be 1. So it's a little bit less work. Again, if you recognize that addition formula, you can apply it. Finding sine of pi over 2 is a little bit quicker and easier than finding the individual values and multiplying and have to deal with common denominators and all that. A problem like number 2, you don't have that luxury of an option as much because if you notice, 110 is not on our unit circle and 20 is not on our unit circle either. So again, for this one, you can't really find those exact values. Instead, we have to recognize what pattern is happening here. We have sine of t, or we'll use s first, sine of s cosine of t minus cosine of s sine of t. So again, notice for this case, it is alternating sine, cosine, cosine, sine. So it's going to be a sine function. And because it's subtraction, remember for sine, they are exact. So sine of s minus t. So that would be sine of 110 minus 20. And now by using this addition formula, we end up noticing that we do get an angle in the inside of sine that is on our unit circle. And again, we know that sine of 90 degrees is just 1. So those are the ways that we can apply those addition formulas to make it a little bit easier to simplify this expression. If they don't give us values, we can still apply this to simplify and reduce. Again, notice we have cosine, cosine, so that's back to back, sine, sine. So if we look at that on our formulas, we know it's going to be a cosine, which would be, they're using s and t, so we're going to hold off on these actually, and we're going to use x and y. So if I say this is x and this is y, cosine, remember because it is a negative, that would be the opposite. So that would be cosine of x plus y. And then all we're going to do here is we're going to substitute. The x goes there. That's the x as well. And then the y, which is t, is going to go right there. So when we rewrite this, we have cosine of, in parentheses, s minus t plus t. And then when we do the inside, notice the negative t and the positive t cancel. So you're left with just cosine of s. So we can also apply these addition formulas when there are no angles given to reduce and simplify any expression where you do have that addition formula pattern. There are times also where on the inside we have a nice angle, but that other angle is either not given or it's not a nice angle. So we can split it using that same formula, but now we're going the other way. So we have cosine of 3 pi over 2 times the cosine of theta. Again, addition means it would be the opposite because we're using a cosine function. So minus sine of 3 pi over 2 sine of theta. And now that it's been split, we know cosine of 3 pi over 2 is going to be 0 times the cosine of theta, so that will cancel, minus sine of 3 pi over 2, which is negative 1, times the sine of theta. Subtracting a negative is plus a positive, so you're left with just sine of theta. So we've made this one a little bit easier by splitting and evaluating for the values that we can and leaving the variables in the areas that we can't. On the back, if you take a look at number 5, if it says find the exact value, again, 75 is not on our unit circle. So now we got to do a little bit of thinking. We got to come up with two angles that are on the unit circle that add or subtract, because it's the addition formulas that add or subtract to get 75. Well, we know 75 is equal to 30 plus 45, where both of these angles are on our unit circle. So we're going to say this is cosine of 30 plus 45 degrees, because that's an equivalent to 75. And now we can apply the addition formula, saying cosine of 30 degrees times the cosine of 45 minus, that's the opposite, sine of 30 degrees times the sine of 45. And now that it's been split, we can find each individual value. So the cosine of 30 degrees is the square root of 3 over 2, because that's the x value at 30 degrees on the unit circle. Cosine of 45 is the square root of 2 over 2, minus sine of 30 is going to be 1/2, and the sine of 45 is again root 2 over 2. We get the square root of 6 over 4 for that first term, minus the square root of 2 over 4 for that second term. And the nice thing here is we do have common denominators. So when you add them together, you end up with the square root of 6 minus the square root of 2 all over 4. These are not like terms in the numerator. They do not have the same radicand, so you have to leave it as that. For number 6, we take a look here. Again, it's going to be a little bit similar because we have a nice angle in here, but it's being added with a variable that you cannot find the value of to add together. We're going to go ahead and split this. So let's go ahead and we'll do this side first. So we have sine of pi over 4 times the cosine of s plus sine of s cosine of pi over 4. So that's the left side. We'll put that in parentheses. And then minus, and then we'll split this right side, sine of pi over 4 cosine of s minus sine of s cosine of pi over 4. And now we just got to do a little distribution. Distribute that negative to both parts of the second parentheses. So we have sine of pi over 4 cosine of s plus sine of s cosine of pi over 4 minus sine of pi over 4 cosine of s plus sine of s cosine of pi over 4. If we look at this after we've distributed, we end up with two terms that are exactly the same. That would be the sine of s cosine of pi over 4, and then sine of s cosine of pi over 4. So that's going to be 2 sine of s cosine of pi over 4. And then we notice that these two, negative sine of s, or negative sine of pi over 4 cosine of s, and sine of pi over 4 cosine of s are opposites, so those two would cancel out. All that we have left to do here is actually evaluate the value of cosine of pi over 4, which we know is the square root of 2 over 2. So when we multiply that by sine of s times 2, the 2's will cancel. So you're finally left with the square root of 2 times the sine of s. So again, in this problem, we need to split the two terms separately, and then we can evaluate once we have a trig function of an angle that we actually know from the unit circle. If we take a look at number 7, for number 7, they're giving you, we have a part A and B, they're giving you sine of angle alpha equals 12 over 13 in quadrant between pi over 2 and pi, so that's going to be quadrant 2. So what we want to do here, in order to find the actual angle alpha, is draw our reference triangle. And when we draw our reference triangle, we know alpha is this full angle, but we're using the reference angle to be able to come up with the trig ratios of that reference angle. So sine of alpha is going to be 12 over 13, so opposite over the hypotenuse. Well, we know that's a Pythagorean triple, so that's going to be negative 5. Again, if you don't know your Pythagorean triples and you didn't recognize that, you can do Pythagorean theorem to find that third side. So that's alpha. For theta, we have it in the quadrant negative 2 pi to negative 3 pi over 2. So again, if we're doing our negative angle measurements, that's going to end up in quadrant 1. So this is theta. We're going to use, again, our reference angle to make that. So cosine would be 7 over 25. And again, this is a Pythagorean triple, so you can find that that third side is 24. And again, if you don't know that that's a Pythagorean triple or you didn't catch it, Pythagorean theorem can help you find that. So now, with having two reference triangles for alpha and theta, we can go ahead and find part A. So it says, let's use red, it says cosine of alpha plus theta. So we're going to go ahead and do our addition formula, which would state that cosine of alpha, cosine of theta, minus, because it's opposite, sine of alpha times the sine of theta. And while we don't actually know these angles, now that we have these diagrams, we can go ahead and actually find the trig ratio of those angles. So we don't need to necessarily know the angle, because we can find the trig ratio of that angle given the diagram based on the given information. So we can say cosine of alpha, when we're talking about alpha here, purple, cosine of alpha here, would be the adjacent over hypotenuse. So we know that this one is going to be negative 5 over 13. And we know that sine of alpha is going to be 12 over 13, because that's also given. And now if we look over at theta, for cosine and sine. We know for theta, we know cosine is 7 over 25, and sine would be 24 over 25. So we have 7 over 25, and then 24 over 25. So again, we're just plugging in, based on those diagrams, sine, cosine of alpha and theta. When we do that, you notice that we have a common denominator because you're multiplying 13 times 25 both times. So that's going to be 325. And in the first numerator, negative 5 times 7 is going to be negative 35. In the second numerator, you're subtracting 288. And then you're just reducing to get negative 323 over 325. On part B, we're going to do the same thing. So we're going to do cosine of alpha minus theta. So again, cosine alpha minus theta would be cosine of alpha times the cosine of theta plus sine of alpha times the sine of theta. And again, we're going to use the diagrams that we've made based on the given information to find the sine and cosine of alpha and theta. So the cosine of alpha we said is negative 5 over 13. The sine of alpha we said was 24 over 25. And then for theta we said cosine was 7 over 25 and sine was 12 over 25. 12 over 13. This time the only difference is we are adding them. So again, a common denominator states that this is 325, negative 35 plus this time 288. We would end up with 253 over 325. So when you have problems where they give you the trig ratio and the angle, the trig ratio of the angle, but they don't give you the angle themselves, you can go ahead and draw that actual trig ratio based on the reference triangle in the correct quadrant, and you can use that information to find other trig ratios that are based on the same angle.